Hello and welcome to the second part of our second lesson in the unit on sine functions in our grade 11 University College math class. So we've just spent some time going over this shape that we've been seeing, or that we looked at yesterday. We recapped with that at the beginning. We looked at this shape, sort of remembered how we developed it, recognized that it is a function, because it passes the vertical line test. We looked at the domain and range, and then we talked about some of the terminology that we're going to be using over the course of this unit. So now we're going to apply that a couple of times, and that's it. That's all we're going to be doing today. So what we have here is, for our first example, we have the function y equals sine x, and that's what we have on the graph. Now the period is the length of time it takes for this to start repeating. So if you can imagine here, we started at 0, and then we went up and down and here. That's where our actual function starts repeating again. I would say that sometimes when we're starting this unit, students will say that the period here is only 180 degrees, since that's when our function gets back to 0 again. I will say though that that is not the completion of our full cycle, because at this point, I just keep changing up my colors here, at this point of 0, what our function's doing is heading sort of upwards. At this point of 0, our function begins heading downwards. So that is not the period. It hasn't started repeating yet. We need to continue all the way along over to this 0, where you'd see that from that 0, our function is heading up again, and that would be the actual end of the cycle, if that makes sense, hopefully. It's not when it hits the same point a second time, it's when the pattern that was established begins repeating. So in this case, our pattern begins repeating at 360 degrees. Now a lot of students ask me, can the period change? And the answer is absolutely. The period can be different depending on what we're talking about. I will say you're going to see 360 a lot in this unit as our period length, just because we don't do a lot of horizontal expansions and compressions like they do in the grade 11 university math class. We don't really do that, so we're not going to be manipulating, expanding or compressing, stretching our horizontal values a lot. A little bit, but not a lot. Okay, so what is our maximum value going to be? Well, if we look over here, our maximum value is about here, and that occurs at +1. So our maximum value is going to be +1. Our minimum value, same idea. I'm going to look for it over here. There it is. And I'm going to just draw it all the way across, and that, of course, is going to be -1 will be our low point, or our minimum value. Now the equilibrium axis, we can do the math on this, but visually, I think it's pretty straightforward to see that if 1 is your highest point, and -1 is your lowest point, then the point that occurs halfway between them is going to be 0. We are going to express that, however, as an axis, as we would with an axis of symmetry. The difference is that this one is going to be a y, in that this axis cuts through the y-axis. So y would equal 0 in this case. That's our equilibrium axis. I'll be pretty picky about that. Future teachers will also be pretty picky about when you're putting any axes like that. You're going to want to make sure that you're not just writing 0, but y equals 0 or x equals 0, depending on what it is that you're articulating, for sure. Lastly, the amplitude is the distance from our equilibrium axis up to our highest point or our lowest point. So again, pretty straightforward to see that going from 0 at our equilibrium axis up to 1 or down to -1 has a value of 1. So that is our amplitude. So there's our first example. We did a lot of that while we were working through the definitions up above, but now you can sort of at least see it in context. Okay, so what about non-theoretical sinusoidal functions? What about sine functions that are mirroring or modeling something that happens in the real world? That's what we're going to look like. That's what we're going to look at here in our second example. So the second example reads, Sarah is sitting in an inner tube in a wave pool. The depth of the water below her in terms of time can be represented by the graph shown below. Okay, so we have a graph here. This is Sarah's height above the bottom of the pool. So let's start banging out some of these terms, some of these definitions, and see how they apply to this question. So we have time, we have height. So what is the period of this function going to be? Well, let's take a look at it. So period, as we know, is when our pattern starts repeating. Here we're starting at 2, we go up, we hit 2 again, but that's not the end because the behavior at 2 is different. We'll continue that on until it hits 2 again, which is right here. That's where it hits 2 again. So if we look down in our graph, we'll see that that happens at 3 seconds. So from 0 seconds to 3 seconds, that's going to be our period. So 3 seconds will suffice. That's how long it takes for the pattern to start repeating. What is our maximum height going to be? So again, I just do this by visual inspection. So it appears that the scale of the ticks on our graph here are going up by 0.2, which means that our highest point is going to be 2.4. As we can see, that lines up right there with our highest point. So 2.4 is going to be our maximum height. And that was measured in meters, so 2.4 meters will be our maximum value. Let's find our minimum height. Same thing, visually I can see it. That's going to be happening over here at 1.6. So 1.6 meters is going to be my minimum height, my minimum value. Now my equilibrium axis, again, you're welcome to do this algebraically. I do recommend doing it visually if you can. So halfway between our maximum and minimum values, we can see that that's going to be 2. It hits here at the beginning, the middle, and the end, and it keeps going. So this would make a really nice equilibrium axis value. So our equilibrium axis is y equals 2. Our amplitude, that's going to be the distance from the equilibrium axis to either the high or low points. So if we look at this, we're going from 2 all the way up to 2.4, or from 2 down to 1.6. So that's going to be an increase, or an amplitude rather, of 0.4. So amplitude is 0.4. Again, it doesn't need a positive or a negative value. You can just sort of leave it like that. Now let's look at our domain. Because this is a real-world function, I think we need to consider that this thing isn't going to continue in both directions forever. It's going to have a limit for sure. I think of note is the fact that it starts at a time of 0. But our graph also does not have an arrow on the end here. So I don't know that we can necessarily assume that that Sarah's experience in the wave pool goes longer than the maximum value listed here, and the maximum value listed here is 9 seconds. So it's a pretty short trip, but that's the data we've been given, so let's articulate that in our domain. So we would start that off, the set of all x, such that, I think x is what we were using. Oh, we weren't given it, oh yeah, there it is at the top. So we'll be using f at x and sine x as sort of our input and outputs there. So we'll say the set of all x, such that x is an element of real numbers. Again, this is our real numbers because it's a continuous line. And now we're going to articulate the lowest point, which is 0, and the highest point, which was 9. And we would say that x would be less than or equal to 9, and 0 will be less than or equal to x. And close up the set notation bracket. So there is our domain. Let's look at our range. Our range, similar in that there will be a limit. The highest point we know is 2.4. The lowest point is 1.6. So everything is going to fall between the highest and lowest point as we're working to figure out what the range is. So let's write that one down. Starts with the set of all y, such that y is an element of real numbers. Again, real numbers because it's a continuous line. Now our low point was 1.6. Our high point was 2.4. So we know that y is less than or equal to 2.4, and 1.6 is less than or equal to x. And so there we have articulated a real-world domain and range for Sarah's experience in the wave pool. That's our learning today. Now, the homework is a worksheet, which is the characteristics of sinusoidal functions. It follows here. If you want the solutions, they're posted on the website, but definitely try to do them on your own. There's just a few questions there, so not a lot of homework in this lesson. And where we're heading next after this is we're going to start to graph these things. So big picture wise in this unit, we're going to be graphing sine functions and make all the same types of transformations that we were doing when we were working with quadratics. So vertical translations, horizontal translations, which we call phase shifts, and we're also going to be expanding and compressing it and reflecting it. All the same stuff we were doing when we were working with quadratics. So that's what's coming up over the next 2 lessons. Make sure you got this terminology down so that when I'm talking about it, you understand what I'm saying, and we'll see you in lesson number 3.